Okay, good. Welcome to this week's 1W-MINDS seminar. Our speaker is Professor Akram Aldroubi, who is a Stevenson Professor in the Department of Mathematics at Vanderbilt University. He received his PhD in mathematics from Carnegie Mellon University. His research focuses on sampling theory, harmonic analysis, approximation theory with applications in signal and image processing. In 2014, Akram was named as an AMS Fellow. He also served in several editorial roles, including the editor-in-chief of the Journal of Sampling Theory, Signal Processing, and Data Analysis, associate editor of the Journal of Fourier Analysis and Applications, and editor of Numerical Functional Analysis and Optimization. And he is also a member of the editor board of the Applied and Numerical Harmonic Analysis series. And Akram, it's your turn.
Well, thank you very much, Long Show. Thank you very much, Mark. Thank you for all the organizers for having me. And, we're here in Nashville. It's cold, but I'm seeing all my friends. It kind of warms my heart, at least that. So today I'm going to be talking about this topic that you can see. Now, what's happened? Sorry, I have to go back and forth again. Okay, so dynamical sampling, source term recovery, and frames. Um, so I will actually start by telling you I'll make some general comments first. Then I will talk about the motivation of the work in dynamical sampling and some various problems. Then I know everybody here, this you have seen a million times. Most of you, maybe some new, maybe some student are not familiar. So I will overview basis and frame in Hilbert spaces, and at least I will set some of the notation. Then I will talk about the specific problem here that I'll be presenting, which is dynamical sampling and the problem of source recovery. So this is how the organization is. Let me just give you a little bit of how this all started, dynamical sampling. So this was inspired by a paper by Yu Lu and Martin Vetterli, and which is right here. And when I read that paper, together with my friend and collaborator Ilya Kristol and my student Jackie Davis, decided to kind of formalize and put some of this work in a more mathematical framework, and that's when dynamical sampling ideas started. So it was inspired by really work of Martin Vetterli, Yu Lu, but others also that have worked with them. Since then, that was around 2013. I have worked with a lot of friends and collaborators, and some of them are here today, students, etc. And here's some of the names. I think all of them. Maybe I forgot a few. I hope not. But some of these people that have worked also on this subject with me. So, but the talk today is actually a talk about that involves two subgroups. So the results I'll show you come from two subgroups of those people that you see here. On the top, so you have Le Gong, which is my current PhD students, and she's finishing up. Rocio Diaz Martin, who was a postdoc and now is at Florida State University. She was postdoc at Vanderbilt with me. And my friend Javad Mashregi, who is at University of Laval. And most of you know my friends and collaborator, Carlos Cabrelli and Ursula Molter from University of Buenos Aires, and Ivan Medri, who is currently at UVA and who is a postdoc at UVA, and who also was my postdoc here for a while. So I'll present work that I have done with them, not all together at the same time, but with several subgroups. So, so let me start by something, and I'm sorry if for some of you you don't need that, but just to set up the notation, and for those of you who are new to this area. So here, H is going to be an infinite dimensional Hilbert space, and B is a subset of the Hilbert space, countable subset. And so Hamel basis is simply B will be a Hamel basis if we can represent every element of the Hilbert space as a finite linear combination of the basis B sub j. This is not a very useful for us because this is a purely algebraic definition of bases, and this for an infinite dimensional Hilbert space is uncountable, and it's not really what we will be using. But so the next type of bases that we can talk about that are a little bit more useful, they involve topology or norm. So this these coefficient B sub j, or these vectors B sub j, is going to form the so-called Schauder bases if we can write every vector in the Hilbert space H as an infinite sum of the series of the Bj uniquely. And the problem with Schauder bases, if we only have Schauder bases, we don't have unconditional convergence. The series could converge conditionally, which means if we actually rearrange the term, this term right here, if we arrange them, the Cj, Hbj, we may get a completely different vector. So the ordering here is very important. And this is not something that in general, we like for the type of things that we do here. We'll see why. Of course, the next best thing, or the best thing in some sense for Hilbert space is an orthonormal basis. So for an orthonormal basis, the coefficient is of course a Schauder basis, but the coefficient are given by the inner product of H and the element of the basis Bj. So the series can be written this way. So every element H can be represented this way. The nice thing about an orthonormal basis it is a conditionally convergent series. Rearranging the term in any way will give you the same vector H, and so it's the so-called unconditional convergence. The next best thing for that is the so-called Rees-basis, and the Rees-basis is simply one way of defining it is simply the image of an orthonormal basis under a bounded invertible operator on H. So Bj will be A times Ej, where Ej is an orthonormal basis. And the Rees bases have the property that any vector H in the Hilbert space H can be represented in terms of the basis, by these inner product H B tilde J. B tilde J is the so-called dual basis. It's unique. And also we can switch Bj and B tilde J, and we have this representation. So, and the nice thing about a Rees basis, similar to the orthonormal basis, it is unconditionally convergent. Rearranging the term of the series doesn't change anything. And this is something that is nice, and it also imply certain stability of reconstruction. We'll talk about sampling. But actually, the part that is the most important for us is the so-called frames. So a set of vectors B sub j in H is called a frame for H if we can find two constants positive such that this inequality hold. A, the norm of H squared, is less than the sum of the inner product squared with the term Bj, and less than equal to B times the norm of H squared. And it's just a definition for now, but this alone allow you to prove that if uh, a, uh, a set of vectors form a frame, then you can, that means they satisfy this inequality, then you can represent every vector H in term of Bj. It looks exactly like a representation in term of respaces. So you have this representation, H B tilde J Bj, or you can switch B tilde J Bj. So what's the difference? The difference is every orthonormal basis or every respaces is a frame, but a frame may be redundant, which means you may have more vectors than you need to represent every vector H. So the representation is not unique. The one nice thing about it is that frames allow you to have conditional and conditional convergence of the series. And this type of idea was introduced by Duffin and Schaefer in in the mid 19th, 20th century. So this concept will be very important for us. Let me just say something about frames. It's a little bit, it's more subtle than being a basis plus extra vectors. There are frames that contain no subset which is a basis for H. And so, and there are some very interesting whole theory about frames and about how redundant they are, etc. But I will not talk about that today. I just want to mention that they will be important for the talk, for the rest of the talk. So we're going to need this concept of frame. And again, every orthonormal or respace is a frame. The converse is not necessarily true because we can have redundancy. So now I will start about this dynamical sampling and dynamical sampling problems. As I said, we started working on that in around 2013, maybe a little bit earlier, 2012, inspired by some work by Vetterli, Yulu, and others in their group. And so I will talk about what we have done to formalize some of the problems in mathematically, and that we call dynamical sampling problems. So let me start by this initial value problem, du dt equal to au plus f plus eta, and initially u of 0 at time t equal to 0 is u naught. And so A is simply a generator of C0 semigroup, and u of t belong to H, f of t and eta belong to H. Those are the source term, and u naught is the initial condition. So we have this initial value problem, and because of its so u is going to be evolved in time because of the sources, if there exists, because of u naught, the initial condition, and there are many problems that we're going to talk that we have tackled, and here are three classes. There are more. So the first class is the time-space trade-off in sampling, and so in this case, we have source term f and eta are 0. The operator A is known, and we sample the solution u to this initial condition. U naught is unknown, so here we want to recover u naught. So we sample the evolving signal u of t, both in time and space, to try to figure out what u naught is. We want to recover u naught by sampling u. But of course, we want to sample u in space as little as possible, and sampling u in time as much as we want. Why we do, and so the condition that we want to find. So how do we sample first of all? So we have the vector u. We sample at ti, and g sub j is a test function that will allow you to sample u, and if g sub j is localized around some spatial location x sub j, you get essentially a space-time sampling. get U of xj of ti. So gj will represent, can be essentially a physical measuring device that you plant at location j, and you can actually uh, use that device to sample in time as many times as you want. And so this is what GJ is. And think about, you don't want too many physical device because they are costly. But actually, you want to use them as much as you want in time because that costs you very little. So the idea is then to trade time sample by by space sample, to have as little space sample as possible, yet be able to recover the initial condition U naught. So this is why this is called time-space trade-off. Other type of problems is when the sources F and eta are zero. I will explain why we have two sources here in a minute. And the unknown is actually the operator A and U naught, the initial condition. And we want to recover A, or at least some characteristic of A, and possibly U naught at the same time or not. But here we want to identify some characteristic of the operator A or A itself. And this is the so-called system identification. Of course, we want to use our space-time sample to do that. The source identification is when you actually A is known, U naught is known, but what is unknown is F and eta. So eta is really kind of a background noise. We don't know much about it, but we know some characteristic of eta. And we are interested really in finding the source F. So F is usually modeled by something, and there is maybe a background. We don't care about it, and we want from these spaced-out sample to recover F. So this is three type of problems that that are basically fits into this dynamical sampling type problems. Today, I'm going to be talking about a specific problem of source identification. And so let me tell you a little bit about the problem here. We have a discrete dynamical system. So n here represent time. It now is actually a bounded operator from H to H. We have a Hilbert space, so X sub n belong to Hilbert space is a bounded operator from H to H, and W is a source term, and we're interested to find W. So let me tell you a little bit at least think of a practical problem where this could model. Suppose you have a city, and suppose you have a smokestack like here. There are four. They are in different positions. They happen to be centered, but they don't have to be centered. They could be one in one corner, another one in the middle. I mean, this is just so the center being centered and kind of bunched together is not the point. But there are smokestacks, and these smokestacks are a specific location, and they are actually spewing some smoke here at a constant rate. So all of them, for the moment, for this particular problem I'm going to present, are releasing smoke at a constant rate. And then of course, because of this concentrate smoke is gonna go all over the town that you have here because of some dynamical system. And so we want to know at each location how much is the amplitude of the smoke that's coming out of the smokestack. So this is what we're going to try to model. And how do we want to try to find out the source, which means the amplitude of the smokes coming from the smokestacks? We're going to put various sampling devices that are here depicted by these meters, 1, 2, 3, 4. We have put 4, but we don't know if we need 4 or more or less. And we're going to actually sample in time at this location the concentration of smoke. And we want to be able to recover how much smoke is coming out of these stacks per minute. So that's essentially one way to think about what we're going to try to do. So the mathematical problem is you have a subspace W in the Hilbert space H and a little vector W in capital W's, and we want to recover little w from measurement x at time n, inner product gj at location j. And so those are the measurements. W is smokestack. There are four of them. So this capital W represent a four, for this problem that you see here on the picture would be a four-dimensional space, subspace. And you have an operator A, which is known, and this is the dynamical system. Xn plus 1 is AXN plus W. And we want to recover W that belongs to this subspace, capital W, from these measurement, X space-time measurement, Xn Gj. So this is the problem. N is bigger or equal to 0. So for time, N is bigger or equal to 0. And the location, J, is our spread in time. So uh, J represents spatial location and represent time. And we're interested in this source from these measurements. So this is again the problem. A belong to a boundary operator of H. W belong to subspace of H. G sub J is a Bessel sequence. That's the assumption. And we want to know under what condition the placement of this GJ, or under what condition GJ can we recover W from the measurement Y and J, which are the space-time measurement right here. So, and we want to recover it in a stable way. And we have to decide what do we mean by stable way. And so this is the problem now that we're looking at. We have a dynamical system and a known W, these space-time sampling that are described by the inner product of X at time N and Gj. And we want to find condition on Gj to be able to recover W in a stable way. And stable, we have to decide what stable means. So the measurement Y and J, which are these inner product, can be organized into a matrix. N time, J space, so it's a two-dimensional matrix. And this matrix right here belong to some set of matrices. I'm call it here script M1, and that's where the data belong to a space of matrices. And we want to now, in order to describe what we mean by stable recovery, means that we want to take our data, which belongs to M1, and find an operator that gives you back the source term W using this operator. And we want it to be less than or equal to some constant, some norm on this matrices. So I have to actually now tell you what kind of norm I put there so that this makes sense. So we have set of matrices, and we have to describe a norm on this set of matrices. And once I do that, I want an operator that will take matrices that come from this space-time sample and bring you back, and we want this norm inequality. And if that happens, we're happy because we are recovering W in a stable way. So this is our definition of stable way. Now I have to be able to tell you, well, okay, we have a set of matrices. What kind of norm do we need that is appropriate to solve this problem? to try to solve this problem. And so the data again is described by a matrix. So x, the vector x at time 1 is sampled at position 1, at position 1 by this inner product x1g1, as position 2 x1g2, etc. And at time 2, we again sample at the position g1 at 1 and 2 and k, and we organize everything in this matrix. And so the data that we have, m sub 1, is a matrix where well, could be finite, infinite, or bi-infinite, but we'll talk about that in a minute. But the norm that we're going to put on this matrix right now is we're going to take each row, take the L2 norm, take the soup of all rows, and that's going to be the norm of M1 that we're going to use. So this is the type of norm we're going to take. And really, I'm going to first talk about source recovery when W equal to all of H. That means, what this means is kind of a silly problem, but this is an important problem because this is how we arrived at understanding what to do with a more interesting problem. So what does it mean to have the source being anywhere in H or W equal to H? What we're saying is in that city that I showed you the map of, there is a smokestack at every point in the city. Every point is kind of spewing some constant type smoke. It's not realistic, of course, but still, we wanted to understand this first. And so we actually, it turns out that we really only need finitely many time samples to solve this problem, and I will explain in a minute. So the matrix that I'm showing you here is finite in time. So there are finitely many rows and infinitely many columns, because we have to actually, we'll see that we'll have to, in order to recover the vector source for this particular problem, you have to actually sample everywhere. It is not interesting in the sense, but it tells you something about it helps us understand the problem. So of course data is always noisy. So the sampling take you from H, which is W, to a set of matrices, and M in principle have more matrices than can be described by the image of S. It's an injective map, but because you have noise, usually you are outside the image of W into the space M, which is, you're always going to assume that you have some noise. So the image of the sampling operator is always a little smaller than D. This is just all what it depicts, which is a good thing because normally we won't allow room for noise. And the first result that we were able to get is that if G sub j is a Bessel sequence in H, then we can find an operator R that takes the data from M1 to H. M1 is this space of matrices with the norm that we've described that allow it to recover the source term if and only if this Bessel sequence is in fact a frame for H, and if you want this inequality right here. So you can find an operator R that will allow you to recover the source term W, and the recovery is continuous with respect to the data norm if and only if GJ is a frame for H. Let me say a little bit what this kind of result it's interesting and not interesting. This kind of result allows us to understand really what kind of norm we have to put on M1. But if you think about it, GJ, if and only if GJ is a frame of for H, what this says is if there is a smokestack at every point of that city that I showed you, and we want to recover how much each smokestack is spewing smoke, we have to measure at every point of that city. And in some sense, this is what this is saying. It's kind of trivial. It's not that interesting, but this is the result. Okay, so for this case, I think the interesting part is that allow us to understand how to put a norm on the space of matrices. In fact, we can show that for the case where W is all of H, where we have a smokestack at every point in that thing, in fact, we only need two time samples. So we put measurement at every point, measuring devices at every point of the city, and we only use two time sample for each device, and that is enough to recover this in a stable way. That's the result here. And before I go on, I just want to tell you about the interesting problem now is where, in fact, the smokestack, which is the natural way, are not positioned at every point in the city. There are few. And so the space W that represent the smokestacks is a subspace, proper subspace of H. It's not equal to H. And here we can show that for this case, actually, first, taking finitely many time sample is usually not possible. You have to, in general, take infinitely many time samples. But so this is the first result that is interesting. If W equal to H, then the result you need only finitely many time samples, but infinitely many spatial samples, and these spatial samples have to form a frame for the Hilbert space H. That means for the problem I told you, you have to plant a sampling device at every point in that in that city, but you only need to activate your sampling device twice. That was the previous theorem. But if you only have finitely many stacks, or the number of smokestacks are not everywhere in the city. So if this condition holds, W is a subset of H, but not equal to H, then in fact, one thing is you need in general infinitely many time steps, and you want to know what happened. Where do you plant your sampling device? So I will not go too much into that particular result right there. All I want to say is, suppose you have four smokestacks, or finitely many smokestacks. That essentially translates into the dimension of the subspace W is 4. If you have 5 smokestacks, well, 5. So the number of smokestacks is coded in the dimension of W. And if the dimension of W is small, which is the typical situation, you want to have fewer measuring sampling devices possible. So you would hope that you would have not many more than 4 measuring devices, which are depicted here by these watch-like thing, the measuring device. There are 4 here and 4 smokestack. You would hope it's not much more. And anyway, there is a minimal set of sampling device, G sub j, that you would need. In fact, you want the cardinality of the number of sampling device, or the cardinality of J, to be as small as possible, or small, but you want to position them in space in such a way you can recover the W, which represent the smoke from the smokestack, or the source. So this is the source recovery becomes really interesting when W is not equal to H. So here we have again to describe the set, the measurement are organized in some matrix. And this matrix is kind of very similar that the one before, except in general, you have to have infinitely many time samples. So the columns are infinite. And you, depending on the dimension of W, if it's infinite or finite, this, the number of rows, the number of columns could be finite or infinite, and the number of rows have to be infinite in general. So we have these type of matrices, and as before, we want to describe a norm on these matrices. So what we do, we took every row, we take the L2 norm of every row, we take the sup over all row, and we want one more condition, which is wasn't present before. We want that the rows converge to some row vector, to some vector in L2 as the rows goes to infinity. So the limit of Ri minus t for some t in L2 must be 0 as I go to infinity. And the norm of such matrices is taken by the sup over I beginning with 0 of the L2 norm of Ri. And we can show that the matrices that have this property, such that their rows converge, and we take this norm, that this is actually a Banach space. So we can prove that M1 with this norm and the type of matrices that satisfy this condition is in fact a Banach space. And this is our Banach space. And now we have a result that says, well, assume that W is subset of the Hilbert space H, not equal to it, and it's closed. And GJ is a Bessel sequence. And now here, the norm of A is less than 1. Then we can find a reconstruction or a recovery operator R from M1 to H that is continuous in this sense. The norm of W in H is less than or equal to constant than the norm of the data in M1, if and only if. So you see now here it's interesting. It's if and only if something is a frame for W. It's not GJ that should be a frame of W. It's something else. You take I minus A star is the adjoint of A, take the inverse of that, apply it to GJ, and that gives you a set of vectors. So, and you take the projection of these vectors on W, that set must form a frame for W. And this is an if and only if condition. So you can recover W if and only if this condition is satisfied. And by the way, it is very possible that GJ is a frame for W, but you cannot recover the vector because this condition is not satisfied. So the right condition when W is not equal to H is this condition, and it reduces to the condition that when W equal to H, that GJ must form a frame for H. And so this was the result for finding recovery of smokestacks in a stable way. I go from smokestacks to, and from this, just this if and only if condition, you get information. If W have dimension R, if the number of smokestacks is R, then we need at least R sampling devices. So the number of sampling devices should be bigger or equal to R. But in principle, it can be, most of the time, it can be exactly R. But that's a condition. We can, it's right here, and it tells you that you cannot recover with fewer, if you have R smokestack, you have at least R measuring device well placed to be able to recover the source W. So this is what this result tells you. And let me go now to a problem which is a little bit more complicated, but it's more realistic. Smokestack are not going to be constant. If you have these smokestacks spewing smoke, in general, maybe they vary maybe periodically in time. Why? Because maybe the factories that are producing this smokestack produces more at night than during the day. Maybe they certain weeks they're producing more than others, etc. So we are think of now the smokestacks are a function of time. So operator A belongs to a bounded operator on H. W is a subspace of H, but now the sources right here depend on N. It's periodic of period capital N. And so we have X at N plus 1 equal to AXN plus W of N. This W is periodic, and we are again just sampling in time by taking inner product of X at time N with G sub J. And again, J represents location and represent time, and we want to recover Wn from these measurements, X and Gj. So this is very similar to the other problem. It just have a periodic source that we want to recover. And so the same question, can we recover it in a stable way from the measurement? And here is again what do we mean by stable way? We have to decide what we mean by stable way. We have to decide how the data that we get from these measurements, what kind of they are matrices, but they have certain structure, and we have to understand the structure of these matrices, and we have to give these matrices a certain norm. And this is so one way of describing this problem is to say, well, the source is periodic of period capital N. So I can identify the source as n vector W0, W1, Wn minus 1 that belong to the Cartesian product of W n times. So we can identify this function of time as a vector in Hilbert in the Cartesian product of W n time. And we have to describe what we mean by the set of measurement Mn and what these matrices look like. And so once we identify that, we want an operator R from this space of matrices to this Cartesian product, W to the power n, such that any W in any vector W in W to the power n can be recovered from some operator that have this condition. Here, I have to tell you what Mn is and what we mean by this norm. So again, we have matrices. How do the matrices look like? So the space of matrices here, again, there are matrices, the Ij, and they look like this. And now the rows have the following property. The set of matrices that we are describing here is not just any set of matrices. It's a set of matrices such that this condition hold. If you take the row, capital N times K, capital N is a period. So this is row nk plus s. The limit as k tends to infinity of this row is some vector in L2. So what this means, let me take the first vector and vector number n and vector number 2n, etc. These have to converge to some vector in L2. Then you take the row 1 and row n plus 1, etc. These have also to converge to some vector in L2, and so on. So this is the type of matrices that we are describing. It's not all matrices. They have certain particularity. And for those matrices, we again define a norm, the soup over the rows, L2 norm of the rows. And we can show that this is a Banach space. And this is the norm that we take on that. Yeah, this is the norm. And this is the type of matrices we need. Why do we have this condition here? After all, we are pushing the source term is periodic. So the data eventually is not exactly periodic, is kind of almost periodic. And this is what this condition is essentially saying. And here's the theorem that says, suppose A is a bounded operator, but it has norm less than 1. And W is a closed subspace of H, and N is an integer, which is the period of our source term, W. Then we can find an operator that will recover this little w in a stable way, which means it satisfies this inequality. If and only if, well, now it looks like almost the same condition as before, except we have capital N of these conditions, and we have this term exponential e to the 2 pi I s over n. So we take the set Gj, which is the Bessel sequence. We apply to it I times e to the 2 pi I s over n minus a star minus 1. This is this operator for each s equal to 0, 1, 2, etc. And we project those vectors, and these, for every s, should form a frame for w in order to be able to find a recovery operator. And this is an if and only if condition. So it's very much like the previous case is just a special case of this. So that is you can see that somehow here we have to use Fourier series in Hilbert spaces. I mean, that's kind of tell you somehow we are using Fourier series in order to get this result. That's what this, you can kind of guess what's happening here. And I will stop here and just simply say, okay, again, if the dimension of W is R, we need at least R sampler. So the number of vectors Gj should be R or more, otherwise we cannot recover. And finally, if you are interested in looking at dynamical sampling, many problems, this or others, we have currently a survey, which we just put an archive not long ago, this summer, and it talks about this problem. Well, it described dynamical sampling in general, all the problems that you can have been solved or open problems in that area, and you can find it in that archive. And you can also find, if you're interested, the papers that correspond to what I've talked about today. So I will stop here and thank you very much.
Thank you for the great talk. Any questions from the audience?